Next, we have an example of a right isosceles triangle where what are the two angles equal to, other than, not the 90, but the other two? They're both 45. So this is also known as a 45, 45, 90 triangle, special right triangle. Now, we know the two legs are equal this time, so we don't really have small, medium, and large. Instead, we have two smalls and a large, okay? So because the two smalls are the same length, this one would have to be 1 as well. The question is, what's the hypotenuse, C? Let's go back to the Pythagorean theorem. What we're going to try to do is come up with a way of figuring out what that other side has to be no matter what, whether the two legs are both 1 or 11 or 12, whatever. We're going to generalize. So I guess instead of using 1, we're going to use A. Let's change those 1s to an A. So we have A squared plus B squared equals C squared, turning into A squared plus A squared equals C squared. You with me? Yeah? Good. How many A squareds do you see? 2A squared equals C squared. This is what we're looking for. We know the A's have to be equal, but how is C related to them? Well, if C squared equals 2A squared, how do you get C by itself? The square root of 2A squared. Is the square root of 2 nice, non-decimal, perfect square? No. Leave it under the radical. Is the A squared square rootable? The square root of A squared is A. It's traditional, this is kind of another little side note for you, to write the variable before the square root for the simple fact that you don't confuse it with the square root of 2A. Square root of 2A is what we have. So you don't confuse the two, we write the A out front, just like with B root 3 or A root 3 in the last problem. All right? So that's the relationship between the sides of a 45, 45, 90 right triangle.